Bismillahirrahmanirrahim. In this video, we will discuss about the boost converter. As the name indicates, it's the converter which is used to step up the DC voltage. So the circuit diagram for the boost converter is shown in front of you. This is our input source. We are going to represent it with VG. Then we use an inductor and a fully controllable switch. This may be a BJT, maybe an IGBT, power BJT or the MOSFET. And here is the control circuit for that one. So control circuit means a circuit consisting of microcontroller or microprocessor, then the amplifier circuit and the isolation circuit, so that we can apply the gate voltage to this switch. So this is represented by this control block. Then we have the diode represented as D and a capacitor and the load resistance R. In the last video we have discussed about the step-up chopper. The circuit is nearly the same except the addition of this capacitor. This is an additional component which is used over here to regulate the voltage at the load terminals. So now this circuit is operated by turning this switch on and off. So it has two modes of operation. The first mode in which your main switch is in the on state, that is this switch. If we are going to turn on this switch by applying the gate voltage, so you can represent it with the short circuit in the ideal case. But in the practical case, there will be a voltage drop, so that can be modeled over here. So considering it an ideal switch, this is the situation that this terminal of the inductor is connected with the reference point or the ground. So we are going to consider that this is the reference point, right? So the equivalent circuit when your switch is in the on state will be looking like this, that your switch is connecting this terminal with the reference point. Now in this case I can say this inductor is in parallel to the source, and the inductor current, that IL of t, that will be equal to IGT, where IGT is the input current. And now if you look at this point, your diode is connected, the anode of the diode is connected with the zero potential, right? So what about this diode? It will be in the off state, it will be reverse biased. So when it will be reverse biased, it means there is no connection between this point and this point, so it is an open circuit. And the load side is shown over here, the capacitor and the resistance. Let's suppose that the voltage across the load is plus minus V naught and the current in the load is I naught T, that is going to flow in the downward direction, and the capacitor current, let's suppose, is in the downward direction, and the value of the capacitance is C. So this is the equivalent circuit on the load side, and this is the equivalent circuit on the source side when your switch is in the on state. Once you are going to turn off your switch by removing the gate voltage, so what is going to happen? Then you are basically interrupting the current in this inductor. The polarity across the inductor was plus minus. When you will interrupt the current in this inductor, so it will resist the change in the current by having the opposite polarity, so that you can see over here this positive and the negative. This is the opposite polarity when your switch is in the off state. So as soon as you will make it off, what is going to happen? The diode will be turned on. Why? Because of this positive voltage, there will be the positive voltage at the anode of this diode. So this will be forward biased, and now it can be replaced with the short circuit that you can see over here. So diode is replaced with the short circuit, so it means this positive voltage is available at this terminal. So the total voltage between point A and point B, let me call this is point A and this is point B, that will be the sum of the supply voltage and the voltage across the inductor. The diode over here has been considered as the short circuit, right? In the second mode of operation, your diode is in the on state, and in the first mode of operation your switch is in the on state. In the second mode, you can say that the switch is over here, but now it is in the open state because you have removed the gate voltage or the base voltage from that source with the help of your control circuit. Okay, now let's analyze these two circuits in the mode 1 and the mode 2 to develop the relationship between the input and the output voltages and the currents of this converter circuit. So the inductor voltage in the first mode of operation is equal to your source voltage. So I can write it like that, VL is equal to LD IL by dt, inductor current, right? So from here I can say that LD IL by dt, that is equal to your source voltage VG, where VL is the inductor voltage and Vg is the source voltage. So I can find out the slope of the current dIL by dt, that will be written as Vg by L. That is the slope of the inductor current. Inductor current, rate of change of the inductor current, that will be defined by Vg by L. Vg is the source voltage, L is the inductance, right? And additionally, I can write over here that that VL is equal to the supply voltage Vg. And what about the capacitor current? The capacitor current, looking at the direction of the current that we have assumed, that it is in the downward direction, which is opposite to your load current I naught T, that has been considered over here in the downward direction. So capacitor current will be the negative of your source current, load current. And how you can evaluate the load current? Load current can be evaluated by dividing the load voltage with the load resistance. So considering the first of all the load current I naught, so I naught of T, that is equal to V naught by R, right? And the capacitor current will be the opposite of that one, because we have assumed it in the downward direction. So that will be equal to minus V naught by R. So this is the equation for the capacitor current in the first mode of operation, right? So let me give them the numbers so that we can use them in the onward slides. So let's suppose that this is equation 1, this is equation 2, and this is equation 3. The first equation for the rate of change of inductor current, second one is for the inductor voltage, and the third one is for the capacitor current. Now for the second mode of operation, in which your main switch is in the off state and diode is in the on state. So first of all, writing the equation for the inductor voltage. On this side you have the voltage Vg, and on this side you have the voltage V0. Inductor voltage polarity is opposite with respect to this case, but we will consider this polarity as the reference one, the inductor voltage. So the inductor voltage can be written as that VL, that is equal to Vg minus V0. And these small letters will be representing the DC average value, plus there is the small ripple in the supply voltage, in the load voltage and inductor voltage. So we these small letters are representing that one. But if I use the capital letters, it means that I am only considering the average values, and the small signal variation has been neglected. So the inductor voltage over here can be written as Vg minus V0. So this is the inductor voltage equation. So let me call it equation 4, right? And now what about the capacitor current? The capacitor current can be written as the load current, inductor current minus the load current. That's the current that is coming from here, from the inductor. So from that, if you subtract the load current, the rest of the current will be passing through the capacitor. So we can write down the equation for the capacitor current, that is IC is equal to IL, that is the inductor current, minus V naught by R. And neglecting the small signal and taking the average values, I can write it IL minus V by R, V naught by R. So the capacitor current is given by this equation, right? So I can write it like that, that IC is equal to IL minus V naught by R. So let me call it equation 5. So that is the equation for the capacitor current. Okay, now what about the inductor current? For inductor current, let's look at the equation of the inductor voltage. So for the second mode of operation, I can say that inductor voltage, that is L dIL by dt, that should be equal to Vg minus V0, right? And from here I can say that dIL by dt, that is equal to Vg minus V0 by inductance. So this is, let's suppose, equation number 6. So we have written 6 equations for the rate of change of current in the inductor in both modes of operation, for the inductor voltage, and for the capacitor current, right? Now let's draw the waveforms for this converter circuit for the two modes of operation. So first of all, let's look at the inductor current waveform. So we have two intervals, one is the on interval and one is the off interval, and this procedure will be repeated. So I'm going to mark these three lines representing these intervals on and off. So assuming that we are operating in the steady state, so our inductor current will be starting from some minimum value I1. So when you are going to turn on the switch in the first mode of operation, your current will be increasing, and let's suppose that finally it becomes equal to I2. That is the maximum current in your inductor in the first mode of operation. And first mode of operation is for the time t on, which is equal to d into ts that we have discussed in the previous videos. Okay, so this t on is equal to dts, and in this interval the current will be passing through this inductor, and your inductor will be acting as the load, and it will store energy, and the stored energy will be given as half Li square. The energy will be pumped into the inductor, right? And during this interval of time, if I ask from you what is the inductor voltage, so inductor is connected in parallel to your source, so inductor average voltage will be equal to the source voltage Vg, because inductor is in parallel to that one. So if I sketch the inductor voltage, I can draw it like that, that it is equal to VL is equal to Vg in this interval of time, and its reference level is, let's suppose, this one, right? So this is the inductor voltage. Let me write down over here VL, and this is the inductor current IL, right? Okay, so in the first mode of operation, we have marked the inductor current and the inductor voltage. Now in the second mode of operation, that is the off interval, when your main switch is in the off state and your diode is in the on state, so here this inductor will act as the source and will deliver the energy that was stored in this cycle to the capacitor and the resistance. So energy stored in the inductor will be dissipated, and what will be the polarity across the load? This point will be positive, polarity across the inductor. This point will be positive and this point will be negative. Why? We have seen in the previous slide that when we are going to interrupt the current through the inductor, so how it is going to resist the change by making its polarity opposite with respect to this one. Over here it was plus minus, and over here it is minus plus, so its polarity is opposite. So inductor polarity will be opposite. And now if you look at the total voltage between the point A and the point B, so that will be equal to the inductor voltage plus minus plus the source voltage. So your net voltage across the load will be equal to source plus the inductor voltage. But what about the inductor? The inductor voltage can be calculated by simply taking the difference of the two voltage across its terminal. So on this side we have Vg, and on this side we have the voltage V0. So if we take the difference of these two, we will get the voltage across the inductor, right? So our reference polarity across the inductor will be like that, plus and the minus on this side. This is the reference polarity, and with respect to that one, we will indicate that now the inductor voltage polarity is opposite. Okay, now let's sketch first of all the current. So in this second mode of operation, the current is the direction of the current through the inductor is same, right? And but it is decreasing. Why? Because the energy stored in the inductor is now being dissipated. The energy was half Li square. Now inductor is going to act as the source. So now if I sketch the inductor current, assuming the linear variation, so I can mark it like this, that it is going to decrease from I2 to I1. This I1 must be same as that of this one for the stable operation. And in the next cycle, when you are going to turn on the inductor on again, it will be increasing to I2, and so on. This will be repeated. So this is the inductor current in the second mode of operation, that is for the time t off, when your main switch is in the off state, and this interval will be d prime into ts, where d prime is equal to 1 minus d, right? So I can also write it 1 minus d into ts. Now what's the inductor voltage in this interval of time? The inductor voltage is negative with respect to the previous one. So and in terms of magnitude, that is equal to Vg minus V0, right? So this is the Vg, this is V0. Vg minus V0 will be the voltage across the inductor, and with respect to this reference that we have considered, it is opposite, right? Because the inductor voltage has reversed, because now it is going to act as the source. So inductor voltage will be represented like this in the second interval, and its magnitude is Vg minus V naught, right? So let me mark it over here like this. So this is the inductor voltage waveform, and in the next cycle when you are going to switch on, so inductor will come in parallel to the source again, and when you are going to turn it off, it will provide the energy that is stored. So it is a periodic waveform. So inductor voltage waveform and the current waveforms are shown in front of you for the two intervals, that is the on interval and the off interval, right? So this is the on one, and this is the off interval, that is equal to d prime into t. Okay, now we know that the average voltage across the inductor should be 0 for its stable operation. So how we can find out the average voltage across the inductor? We will have to look at this area. This net area uncovered by this inductor voltage waveform should be equal to 0. This one is the positive area, and this one is the negative area. So positive area and negative area must be equal to each other. That is the volt second balance for the inductor. So now if we write down the volt second balance equation, volt second balance for the inductor, so I can write down it like that the area covered over here in the positive voltage across the inductor, so what that will be equal to, the height is VL and this width is equal to T on, right? So I can write that inductor voltage, that is equal to Vg, in this case Vg into T on, right, plus the inductor voltage, that is Vg minus V naught, and for the time t off, that should be equal to 0. This area should be equal to 0, right? So now I can write it like this, that it is Vg into T on can be written in terms of duty cycle and the total time, that is equal to dTs, right? This on time, dTs, plus Vg minus V naught into T off, and T off is equal to D prime into Ts. So we can write this equation like this, and now we can simplify this equation. Vgts plus Vg into D prime into Ts minus V naught into D prime into Ts, so that will be equal to 0. And so from here, if I look at this part, Vg, so Vg into Ts, this can be written as D plus D prime, that will be equal to V naught into D prime into Ts. So dividing both sides by Ts, we are going to get that Vg Ts will be cancelled out, and D plus D prime is 1. So Vg will be equal to V naught into D prime, and from here I can say that V naught will be equal to Vg divided by D prime. And what is the range for the D prime? D prime is less than 1, right? So it means that our output voltage will be higher than the input voltage. So this is the boost converter, because it is going to give you the higher voltage at the output. So V naught will be higher than the source voltage Vg, and that's why we call it the boost converter. And why it will be higher? Because you can see over here, your inductor is in series with the source, and the net voltage between point A and point B is higher than your source voltage, because your capacitor will be charged to this higher voltage, that is equal to the inductor voltage plus the source voltage, and then it will retain that voltage across the load resistance. So you will be getting the higher voltage at the output. Okay, now what is the average inductor voltage? So average inductor voltage will be sketched like this. So let's suppose this is IL, and these two brackets will be indicating the average value. So the slope of the inductor in the first mode of operation over here, what is this one? If you go back and look at this expression, we have worked for the slope. So slope is equal to Vg by L. So I can say the slope of the inductor current in the first mode of operation is equal to Vg by L, and the slope of the inductor current in the second mode of operation is Vg minus V naught by L. We have worked out these equations in the last slide, right? So this slope is the positive one in this region, and in the second region, in the off state, the slope is the negative one and is given as Vg minus V. So Vg minus V naught, and V naught, as you know, that is higher than the input voltage. So this, there is no negative sign over here, but it is hidden inside. That is Vg minus V naught. V naught is the higher one, so the net result will be the negative one. So the inductor current waveform that we have seen in the last slide is shown over here. Now let's assume that the variation in the inductor current, that is this one starting from I1 to I2, that is equal to 2IL, right? So with this we will be working for the ripple in the inductor current. So let's assume that that is equal to 2 delta I, and the average value of the inductor current is this one, IL. Okay, so the delta I is above this line, that is this part, and the delta I is below this average line and the minimum value. So sum of these two is the 2 delta I. So total ripple in the inductor current waveform is assumed to be 2 delta I. So now for the calculation of the inductance, we are going to use the expression for the slope. How you determine the slope? Slope is delta y by delta x. So we can say that delta y is equal to slope into delta x. So what is delta y in this case? Delta y is the change in the y-axis quantity, and that is the inductor current. So that is equal to 2 delta I. So 2 delta I will be equal to the slope multiplied with delta x. So what is the slope in the first mode of operation? In the first mode of operation over here, the slope is Vg by L. So taking this slope from here, so Vg by L into delta x. What is the delta x for the first mode of operation? From this point till this point, that is equal to T on. So I can write it like this, and from here I can say that delta I will be equal to Vg by 2L into dts, because T on is equal to dts. So delta I can be written as Vg into d divided by 2L into Fs. So what is Fs? Fs is the switching frequency, that is the inverse of the time period Ts, right? So the delta I, that is the ripple current of your inductor, can be represented in terms of the supply voltage with the help of this expression. You can also represent it in terms of the output voltage, because you know the relationship now between the input and the output voltage. So your output voltage is equal to Vg by d prime. So from here you can see that Vg is equal to V naught into d prime. So if I call it equation A, so from equation A, I can write that delta I will be equal to Vg into d, and Vg is equal to now V naught into d prime. So V naught into d prime into d divided by 2L into Fs. So delta I can now be written as is given by this equation in terms of the output voltage. So you can represent the delta I in terms of the output voltage or in terms of the input voltage. So in terms of input voltage, it is given by equation A, and in terms of output voltage, it is given by equation B. All of these are the circuit parameters. The D depends upon the control signal, and that is defined as the ratio of the on time with the total time, that is the duty cycle, right? So using looking at the control signal, you can define that what is the duty cycle. Ts is the inverse of the switching frequency. Switching frequency is decided by your microcontroller. V naught is the output voltage. L is the inductance of your circuit. So you can now analyze, if you know these parameters for your converter circuit, you can analyze what will be the current ripple. The total current ripple will be equal to 2 into delta I. Delta I is the half of the current ripple that is above this average line. This is the average line, and the variation from average line up to the maximum point is delta I, and the variation in the downward direction is delta I. So this equation will be used for the analysis. You can rearrange these equations, and you can write down the expression for the calculation of the inductance. So inductance can be written as Vg into d divided by 2L into delta I, right? So if you know that what should be the current ripple when you are designing the circuit, let's suppose I said the current ripple should not be more than 2%. So how to work out for the value of the inductance? So you will have to rearrange this expression, right? And you know the switching frequency, you know the So you know about these parameters, switching frequency, delta I, Vg and D, so you can work out for the value of the inductance. So now you can design the inductance, and you can do the analysis. It depends upon you. For the analysis, you will be using this equation, and for the design, you will be using this equation. Now let us discuss about the critical value of the inductance. You have seen the inductor current waveform that is shown like this. Now if you are decreasing the inductance, so the ripple in the current will be increasing, and that you can see from here that delta I is inversely proportional to the inductance. So if the and the vice versa, we can say that from, if you look at this one, that if you are decreasing inductance, this delta I, the current ripple will be increasing. So now if you decrease inductance, so this waveform will be changing like this, so it can be represented like this. So at one particular value of the inductance, the current waveform may be represented like this, that it is just right touching the 0 point over here by the end of the cycle. So far in this range, we can say that inductor current is continuous because it was not touching the 0. But once you decrease the inductance below a certain level, so the final result may be like that it is starting from 0 up to this point, and then it is going to reach starting from 0 going to the maximum value, and then coming back to the 0 before the end of the cycle. So in this case, we said that is DCM, discontinuous conduction mode. Your current is discontinuous because it is reaching to the 0 1. But when you are changing the inductance starting from this curve, the green one, then shifting to the blue one, and then to this yellow one, so when you will reach to this point, you are just at the verge of the discontinuity. From here, if you decrease the inductance, your current will become discontinuous. So we can define a condition of the boundary switching from CCM to DCM. CCM means continuous conduction mode. So this is CCM, means your current is above 0, it is not going to reach to the 0. So now what is happening now? Just look at that one. This part is equal to delta I, as we have seen in the last lecture, and this part is also equal to delta I, right? Because we have assumed that the ripple current, that is delta I above this one, and the delta I below this one, below the average line. This is the 2 delta I is the total ripple, right? So this distance is delta I. When the ripple will be increasing, so this waveform will be going down, and you can see over here delta I is increased, and finally it is going to become equal to uh, average value. This is the average value of your inductor. So when delta I becomes equal to the average value, it means you are going to touch to the 0 line, and this continuity is going to start. So now if I say the delta I is over here, then the delta I will be in the upward direction as well. So 2 delta I will be equal to 2 times the average current. So I can write down this expression that 2 delta I L should be equal to 2 times the average value of the inductor current when you are entering from CCM to the DCM, that is continuous conduction mode, to the discontinuous conduction mode. Continuous conduction mode means your current was continuous, and DCM means it is discontinuous. So when you have this condition, when your average current, twice of the average current, is 2 times the ripple current delta I, then you will be right in the boundary. So we have this condition when entering from CCM to the DCM mode. So inductor average current is the source average current. Why? Because if I go back and look at this part over here, you can see in the first mode of operation, the current is increasing through the inductor, and it is being provided by your source. And in the second mode of operation, your inductor and source, they are connected with the load, and the current in this loop will be same. So the current which is passing through the inductor, that is exactly same which is passing through your source. Either it is the source mode 1 or it is mode 2. So your inductor current is basically the source current as well. So average value of your inductor current will be equal to the average value of your source current. So that's why we can write down this expression that delta I, average current of your inductor, that is equal to IL, that is equal to Ig as well. So using this, I can say that 2 delta IL, that is the variation in the inductor current, that is equal to the 2 times the Ig from here for this condition, right? Okay, now let's look at that which portion of the source current is contributing towards the output. If I go back and look at this slide, The inductor current is equal to the source current, no doubt, in both cases, but in the second mode of operation, your inductor and source combined together, they are contributing the current towards the capacitor and the load resistance. There will be the average current through this load resistance, and the high frequency current will pass through this capacitor, because for high frequency the capacitor offers very low reactance. So high frequency component, that is the variation in this one delta I or 2 delta I over here, that is at the switching frequency, that will be passing through this one, and the average current will be passing through your load. So your supply is contributing towards the load current in the second mode of operation. In the first mode of operation, the supply current is purely the inductive current. In the second mode of operation, supply current is the inductive current, and that current is further divided into two parts, capacitor current and the load current. So the supply is contributing towards the output, towards the load in the second mode of operation. So now if I want to look at the contribution of the supply current towards the output, so I can say the supply is only contributing towards the output in the second mode of operation when the current through the inductor or the source is this one, right? So this is either the inductor current or the source current. So only this portion is there at the output from your source. So what is the average current now? So average current at the load in terms of the input current, right? So only this portion is there for the time t on. There is no contribution at the output from your source directly, but it is contributing in the interval d prime into ts. So in order to look at the average current contribution at the output linked with the input, so that will be linked by this d prime, right? So we can say that I naught by Ig, that will be equal to d prime, or I naught will be equal to d prime into Ig, where Ig is the average current of your source. But out of that, only the d prime portion is contributing at the output. So if I look at the average current of the source, that can be represented like this, right? So this is the average current of your inductor, that is the average current of your source, but out of that, just observe this part, that only this portion is going to appear across the load. So relating load current with the source current, you will be using this equation, that I naught is equal to d prime times Ig, because d prime is the interval or the duty cycle of duty cycle that is deciding that what should be the voltage, what should be the current at the output, how much current of the input will be moving towards the contributing towards the output, right? Okay, now let's work out the critical value of the inductance. So 2 delta IL, that will be equal to 2 times the average current of your source. So this can be now written in terms of the load current, that it is equal to I naught by d prime. And what is the I naught? I naught is the average current at your load, right? So average current at the load over here, how to calculate that one? I naught, that will be equal to V naught by the resistance R, that's the average current. So we can use this expression over here, and we can write it like that, that this is equal to 2 V naught by R into d prime. And we have worked out the expression for delta I. Either you can use the equation A or you can use the equation B. Both are going to represent the delta I, this one or this one. So let's use the equation A. So equation A used over here, so we can write it like that, that 2 into Vg into D divided by 2 into inductance into the switching frequency, that should be equal to 2 times the V naught divided by R into D prime. Over here I will represent this inductance as the critical inductance, because we have used this condition that 2 times of the current ripple delta I should be equal to 2 times the average value. At that point there will be the transition from continuous conduction mode to the discontinuous conduction mode. So this inductance will be called the critical inductance. So now simplifying this, we can write it that this is equal to d by 2 LC into Fs, that is equal to 1 by R into d prime square, right? And now finally I can say that LC will be equal to R into d prime square, into D divided by 2 into Fs. So this is the expression for the calculation of the critical inductance. So what is done over here, this V naught, I have represented this V naught in terms of Vg so that we can cancel this one with this one. So we can also write it like this, that this is equal to uh, 2 into Vg divided by d prime into r into d prime. So Vg and Vg from both sides will be cancelled out and you will get this expression. So what is the importance of the critical inductance? If you are designing your circuit and you keep your inductance of your circuit higher than the LC, so then your circuit will be operating in the continuous conduction mode, and if your inductance is less than the critical inductance, so your circuit will be operating in the discontinuous conduction mode. So looking at the critical value and comparing it with the actual value of the inductance, you can say that either your circuit is operating in the continuous or in the discontinuous conduction mode. So it depends upon the circuit parameter. So so far we have analyzed the circuit in detail and we have worked out for the value of the inductance, critical inductance, and we have seen the current ripple. Now we are going to look at for the capacitor, because the capacitor is the one that is connected in parallel to the load, and the capacitor voltage will be exactly the load voltage. So variation in the capacitor voltage will be reflected in the load voltage, and that will be the voltage ripple at the load. So now let's look at the capacitor current waveforms so that we can define procedure for the design of the capacitance for the particular requirements. Now let's look at the two modes of operation for the circuit. Mode 1, in which your switch is in the on state, and the mode 2, in which your diode is in the on state, and we sketch the capacitor current and the voltage waveform, right? So let's sketch them. So in first mode of operation, we just look at this part. The capacitor current is in the downward direction, that is the reference polarity, but it is going to provide the current to the load, and if the load polarity is plus minus, then it should be in this direction, right, from the top to bottom in the load. So it means that the slope of the capacitive current with respect to our reference will be the -1, right? So the capacitor current will be the -1 with respect to this one. So I am going to sketch it like that this is equal to minus V naught by R, and the average capacitor current in this interval. And in the second interval, the capacitor is charging. And what will be the capacitor current? So total current is this one IL, that is the inductor current. Out of that, the average current at the output is I naught, so average current through the capacitor is IC. So from here I can say that this capacitor current IC will be equal to the inductor current minus the load average current I naught, right? So from here I can say inductor average current minus V naught by R, because the load average current can be determined with the help of this expression. So from here I can mark that this current IL minus V naught by R is the current through the capacitor, right? And that should be of opposite polarity, because the average current through the inductor through average current through the capacitor should be equal to 0. And again, when the cycle will be repeated, this will be equal to minus V naught by R. And then in the second cycle, it is the current in the direction of the assumed reference polarity IC. So it is in the same direction, so we have considered it positive. So this is the capacitor current waveform. Now let's look at the capacitor voltage. So in the first mode of operation, the capacitor is providing the energy to the load, so its voltage will be decreasing because the charge stored over the capacitor will be reduced. So its voltage will be changing like that. Let's suppose this is V2, and finally it is going to become Vn by the end of the cycle. At the end of the cycle, when you are entering into the second mode of operation, your capacitor will start getting charges. So now the voltage across your capacitor will be improving, or the voltage across your load will be improving or increasing because it is being charged, right? So this will be the capacitor voltage waveform. Ideally speaking, it would have been a straight line if you are talking about the constant DC. So average value of the capacitor voltage is this one, VC this. right, and that is equal to the average voltage across the load, because the voltage is capacitor is connected across the load. Okay, so what is the slope of the voltage variation? How you can determine this slope? So first of all, let's consider the mode 1. So for mode 1, we can say that Vc by dt into the capacitance, that is equal to your capacitor current, right? And so from here I can write that dVc by dt, that is equal to the capacitor current divided by the capacitance. So that is the slope of the voltage, rate of change of voltage in the across the capacitor. And in terms of the average parameters, I can write it like that, that this is the average capacitor current divided by the capacitance. So average capacitor current now can be written like that, that it is equal to V naught by R, so divide by C, so you will get the expression for the dVc by dt. So why we have considered average capacitor current is equal to V naught by R? Because you can see in this mode of operation, in the first mode, the capacitor current is equal to your load current. So whatever will be the average current at the load, the same current will be there through the capacitor. So average current through the load will be obtained as V naught by R. So that's why we have considered the average capacitor current is V naught by R in the first mode of operation. So this is the expression for the slope of the capacitor voltage in the first mode of operation. So we should write it like that, that this is equal to V naught by RC. Now let's work out the slope of the voltage in the second mode of operation. So mode 2, in this case I can say that dVc by dt, capacitor voltage, that is the derivative of the capacitor voltage into the C, that will be equal to the capacitor current IC, right? And what is the capacitor current? Capacitor current is equal to the inductor current minus the load current. So from here, in terms of the average values, I can write that C dVc by dt, that is equal to average value of the inductor current minus the average load current, right? And finally I can write that this is dVc by dt, the rate of change of current is dVc by dt, that is equal to IL minus I naught divided by the capacitance, where IL is the average current of the inductor, I naught is the average current at the output, divided by C. So when we are dividing the C on the right side, so that will be removed from here. Okay, now what about the inductor current and the source current? Inductor average current and the source current, they are same, as we have already seen. So we can write that dVc by dt can be written like this, that Ig minus I naught divided by the capacitance. So this is the slope of the uh, capacitor voltage waveform in the second mode of operation. So let's mark it over on the waveform, so that this this slope, this is equal to IL minus I naught by C, or in terms of the source current I can say Ig minus I naught by C, right? So Ig and IL in terms of average value, they are same, right? So we have defined the slopes for the capacitor voltage waveform. Now the average current through the capacitor should be equal to 0, that you know from the basic operation of the capacitor. So the area under this waveform should be equal to 0, right, considering one cycle. So in the converter, this average area should be equal to 0. So now we are basically applying the ampere second balance. Ampere second balance for the capacitor should be equal to 0. That means the area under the current waveform should be equal to 0. So how to determine the area? That we can write minus V naught by R, that is the height of this portion, multiply by dTs or T on. You will get the area in the first interval, and then in the second interval the current is IL minus V naught by R, multiplying it by T off. So its sum should be equal to 0. So we have this ampere second balance equation. So now let's expand this one by taking the value of T on and T off, and we can write it like this, that is minus V naught by R into T on plus IL minus V naught by R into T off, that is equal to 0, and the T on is equal to dTs. So I can write it minus V naught by R into dTs plus IL minus V naught by R into D prime into Ts. That should be equal to 0. And rearranging this equation, I can or expanding this equation, I can write it like that. This is minus V naught by R into D prime into Ts, that will be equal to minus IL into D prime into Ts. So from here I can write minus V naught by R into Ts into D plus D prime, that should be equal to minus IL into D prime into Ts. So from here V naught by R will be equal to IL into D prime, and the I naught will be equal to IL into D prime, because V naught by R is equal to I naught. So this is the relationship between the output current and the load current. So I naught by IL, that is equal to D prime, right? So from the ampere second balance, you are looking for the relationship between the output voltage and output current and the inductor current. And what is the inductor current? Inductor current is your input current, so I can also write it at I naught by Ig, that is equal to D prime. And we have worked it for the in the previous slide as well, because the input current is only contributing for the second interval, for T off interval. So that's why the output current is D prime times the input current. So that you can also write down from here. I naught is equal to Ig into D prime, because your inductor current is the input current. Your inductor is only contributing, source is only contributing for the D prime interval at the output. Okay, so from ampere second balance, we have related the source current and the load current. Now we are going to work out for the voltage ripple. So for voltage ripple, we are going to look at this waveform again. So over here we can say that the slope is equal to delta y by delta x, right? And delta y is, let's suppose this is this one, and that is equal to 2 delta vc, twice of the 2 times of the delta vc. And the average value of the capacitor voltage is this one. Delta vc is the difference between the average value and the peak value, and the delta vc is the difference between the average value and the minimum value. So total difference is 2 delta vc, that is the variation in the capacitor voltage. So now we are going to work out for that one. So we are going to use the basic expression that delta y is equal to slope into delta x, right? So delta y is 2 times the delta vc. Now let's consider the on interval. So in the on interval, what is the slope? In on interval, the slope is V naught by RC, right? So we can write it like that: V naught by RC into delta x, and delta x is the T on. So from here I can see that delta VC will be equal to V naught by 2RC into D into TS, because on interval is in terms of the duty cycle is written like that. So delta Vc, that will be equal to V naught into D divided by 2RC into Fs, where Fs is the switching frequency and is equal to 1 by Ts, right? So what is V naught by R? V naught by R over here can be written in terms of the current. So I can say delta Vc is equal to I naught into D divided by 2CFS. So you can also write the current, voltage ripple in terms of the load current. Load current is I naught. So this is the analysis equation. And for the design of the capacitance based upon the given parameters, you can rearrange and you can write it that C is equal to I naught into D divided by 2Fs into delta Vc. So if the required voltage variation is given to you, and for the particular load current and switching frequency and the duty cycle, you can find out the required value of the capacitance. You can also work it in terms of the output voltage using the equation, this one. So from here I can say that the capacitance will be equal to V naught into D divided by 2R into Fs into delta Vc. And delta Vc is basically the load voltage. So that is the capacitor voltage variation, or that will be equal to the load voltage variation. Because your capacitor is connected in parallel to your load resistance. So whatever voltage variation will be there in the capacitor, same voltage variation will be there in the at the output. So V naught of T, that is equal to Vc of T, right? So using this you can find out the capacitor value that is required for the particular voltage ripple, or if the circuit parameters are known, you can work out what will be the voltage ripple in the converter output voltage waveform. And if I go back and look at this waveform over here for the capacitor voltage, so if you decrease the capacitor, so variation in the capacitor voltage will be increasing. So at one particular instant of time for certain duty cycle, or maybe based upon load condition or based upon the capacitor value, you can reach to the 0 point over here, right? And if you further decrease the capacitance, there will be the discontinuity in the capacitor voltage. So we can use the same condition that we used for the inductor current, that is 2 times of the average value of the inductor current should be equal to 2 times the delta IL, right? So or the total current ripple, that is equal to 2 delta IL, should be equal to twice of the average value right at the point of the continuity. So using the same condition for the capacitor, so I can write that mm, that 2 times delta Vc should be equal to 2 times the average value of the capacitor, and I can write that 2 times of delta Vc will be equal to 2 times of the average value of the output, because capacitor is connected across the load. So I can also write it that this is equal to 2 into I naught into R. I naught is the load current into the resistance, so that will give you the average voltage across the load. So this now I can write 2 into I naught into D by 2 into C into Fs, that should be equal to 2 into I naught into R. So from where we have taken this delta Vc? Delta Vc is taken from this expression, right? This one, right? So now what is this capacitance? This is basically the critical capacitance, because we have the condition when the circuit is entering from CCM mode to the DCM mode. So this will be the critical capacitance. So simplifying this one, I can write it like that D divided by 2 critical capacitance into Fs, that will be equal to R. I naught will be cancelled out from both sides, and rearranging for the critical capacitance, I can write it that this will be equal to D divided by 2R into Fs. So this is the expression for the critical capacitance. So we have seen that for the how we can calculate the critical capacitance. In this slide we have seen that how we can find out the voltage ripple, and if the circuit parameters are given, and if we are designing the circuit, then how we can find out the capacitance. So we have derived the relationship between input and the output current, and we have seen the different modes of operation: capacitor current waveform, capacitor voltage waveform, critical inductance, inductance waveforms, inductor current, and the inductor voltage waveform for this boost converter. So if I summarize, we have discussed the boost converter in detail, and after this I assume that you should be able to design the inductance and the capacitance for your boost converter, right? We have seen the method for that one. If you know the circuit parameters, you can work out the values for these ones. And how to work out the values for the how to find out the specification of the switch. Of course, this switch is conducting only for the time t on. So for looking at the inductor current, this portion will be the first part will be passing through the switch, so taking the average value. So how to find out the average value? Inductor current is basically your source current, so source current only in terms of on interval is passing through the switch S, right? So for switch S, I can say that the average current will be equal to D times the IG, because the total current is IG, and out of that, for the D interval or the on interval, you have the switch current. So I am going to mark it I S1, that is the current through the switch. So that can be worked with the help of this expression. Okay, so you can find out the average current rating for this switch, and definitely in the practical case you will be having a safety margin of 25% at least, so you will be selecting the current rating as slightly higher than that one. And what is the switching frequency, that you know from the control part. And similarly for this diode, the switching frequency is very important. It should be a fast diode. Its recovery time should be very small, so that it can be turned on within very short interval of time, and can help to deliver this energy stored in the inductor to your load. So the current rating of this diode can be evaluated by looking at the off interval, because it is contributing in the off interval only. So for the diode current ID, I can say roughly this is equal to D prime times Ig, because this is from the off interval of the switch, right? And now you can look at the you have calculated the current of this diode, and you have looked for the current of the switch. We have seen inductor and capacitance previously. So if I summarize and conclude this video, we have worked for the boost converter in detail. We have seen its operation, we have seen that how we can design that one, and how we can select the circuit components. So that's all from this video. Thank you very much.